Okay, so now I start to talk about quadratic residues and quadratic non-residues and Legendre symbol. See. So for quadratic residues and quadratic non-residues, the definition is very simple. A number is a quadratic residue modulo a given prime p if it's congruent to a square. Say, we restrict our discussion to congruencies modulo prime numbers. So let's say we take a prime p. Let p be a prime. And let a be any integer. I say it belongs to a set of integers. Maybe positive or negative, doesn't matter. Let's say the number, it's not, this number is not a multiple of p. A relatively prime. The greatest common divisor is 1. Say 1 says that A is a quadratic residue and I'm going to write just QR for quadratic residue mod p or modulo p if A is congruent to a square. So if there exists a square of an integer number that's congruent to A. So if there exists an integer let's say b such that A is congruent to b squared. Otherwise, we say that A is a quadratic non-residue. So that's their terminology that people use. Quadratic non-residue means, in fact, that it's not a quadratic residue. So we say A is a quadratic non-residue if this congruence does not have any solution. In the sense that if there is no b such that b squared is congruent to A. No integer b such that b squared congruent to A mod p. Now, let's see an example. I'm going to remove everything that's on the board. Now let's say I take p to be 11. I want to list all the quadratic residues and all the quadratic non-residues. So, quadratic residues mod p, or mod 11 in this case. Quadratic non-residues mod 11. How do I find them? I make a list. Say B, and I compute b squared. take numbers, say, be it relatively prime with 11. So numbers, say, from 1 to 10. Compute their squares, modulo p, mod 11 in this case. 1 squared is 1, 10 is also congruent to minus 1, 9 is congruent to minus 2, 8 is minus 3, this is minus 4, minus 5. So already notice that these numbers will be symmetrically distributed here. So I'm going to have actually 5 values, and these numbers will be quadratic residues. 1, 4, 3 squared is 9, 4 squared is 16, 16 is congruent to 5, mod 11, and the next one is 25. Okay, 22 is a multiple 11, 25 minus 22 is 3. And then minus 5 squared is still congruent to 5 squares, congruent to 3. Minus 4 squared is congruent to 5, and so on. Same numbers in reverse order. 3, 5, 9, 4, 1. If we continue and take other numbers, other integer numbers b, square them, those numbers will be congruent mod 11 to one of these numbers. So these are all congruent to 0. If I take a b that's a multiple of 11, its square is a multiple of 11, so I can get 0. And these numbers. So these numbers are the only quadratic residues, mod 11. Let's put them in order. Make a list, quadratic residues mod 11. 1, 3, 4, 5, 1, 3, 4, 5, and 9. Quadratic non-residues, all the integers that are not congruent, all the integers that are not divisible by p, they are relatively prime with p, and they are not on this list. So 2, 3, 4, 5, 6, 7, 8, and 10. And larger numbers. A larger number that's congruent to one of these is a quadratic non-residue, and the other number that's congruent to one of these is a quadratic residue. Now in the interval from 1 to p minus 1, so from 1 to 10 in this case, there are exactly 5 quadratic residues and 5 quadratic non-residues. So there are just as many. Let's write it. Let's state this as a theorem. But let's see why this happens. So let's write this theorem. There are p minus 1 over 2 quadratic residues and p minus 1 over 2 quadratic non-residues. And now a simple, of course there are infinitely many quadratic residues as we notice, but in any interval of length p, there are exactly p minus 1 over 2 quadratic residues and p minus 1 over 2 quadratic non-residues. And the reason is that if I look at these numbers, if I look at numbers, say, if I take two numbers, b1 and b2, between 1 and say p minus 1 over 2, p minus 1, the whole thing divided by 2. In the first half of the interval, b1, b2. If I square these numbers, they will never be congruent to each other modulo p. So if b1 is larger than or equal to 1, strictly less than b2, less than or equal to p minus 1 over 2, in this first half of the interval, from 1 to p, b1 square, which one is larger? Let's say b2 square minus b1 square, b2 square minus b1 square, it's never a multiple of p, because if p divides this expression, then this is a difference of two squares. I can write as b2 minus b1 times b2 times b2 plus b1, so p will divide the difference, b2 minus b1, or b2 plus b1. P being the prime, it has to divide one of those two. But P cannot divide b2 minus b1, because b2 minus b1, it's smaller than the length of the interval, which is less than p. But also, P cannot divide b1 plus b2, the sum. Because again, these two numbers are numbers less than p over 2. And so at most p minus 1 over 2, if I add two such numbers, the sum is less than or equal to p minus 1. So it cannot be a multiple of p. And because it cannot be a multiple of p, then the two numbers cannot be congruent to each other mod p. So that's all we need in order to conclude that indeed the squares of these numbers from 1 to p minus 1 over 2 are not congruent to each other. Then we know that in the second half of the interval, those squares are congruent to these squares, as we saw in the previous example, because 1 and minus 1 have the same square, 2 and minus 2, 3 and minus 3, and so on. So this tells us exactly that there are exactly p minus 1 over 2 squares. In other words, we have a proof for this theorem. Half and half. Now, how can we solve a problem in which we're not required to solve a congruence, but the number is given and we are asked to say, is this number a quadratic residue or a quadratic non-residue? Mod P. Let's see. In other words, is the congruence solvable? So let's see what we have so far. I'll write here what we know. See. First of all, introduce this Legendre symbol. And P is the prime. A is an integer, not a multiple of P. The greatest common divisor is 1. This is the context. And then we define the symbol, the Legendre symbol, as follows. We say it's 1 or minus 1. So A over P, but it's not division, it's just this quadratic symbol, or the Legendre symbol, if you know. A over P, this symbol, is 1 if A is a quadratic residue, and we define the symbol to be minus 1 if A is a quadratic non-residue. It's very simple. So in other words, the Legendre symbol is 1 if there is a B whose square is congruent to A. So in other words, this is also equivalent to say that the congruence congruence x squared congruent to A mod P, the congruence x squared congruent to A mod P, has solutions. There is a B that's a solution, in other words. The congruence has solutions. People write in this way. The congruence is solvable. And if the congruence is not solvable, then A is a quadratic non-residue. So A is a quadratic non-residue. This thing is equivalent to saying that the congruence x squared congruent to A mod P is not solvable. In other words, it doesn't have solutions. It's not solvable. Some natural questions that we ask sometimes, for instance, when we take our exams, questions are of this form. It's an example. Example of a question is, let's say, 73 a quadratic residue mod 37, question mark. Well, is 73 a quadratic residue? Well, it's a quadratic residue if the symbol is 1. And it's a quadratic non-residue if the symbol is -1. So how I solve the problem? I just compute. I say compute the symbol. What symbol? 73, say over 37. 73 modulo 37. This Legendre symbol. Compute this. And if we find that this is equal to 1, then the answer is yes. 73 is a quadratic residue. If the answer is -1, this is a quadratic non-residue. I can ask exactly the same question in a different form. I can say, is the congruence solvable? Is the congruence x squared congruent to 73 mod 37 solvable? Question mark. Is the congruence x squared congruent to 73 modulo 37 solvable? That's exactly the same question. I compute the same symbol. Compute same symbol, 73, 37, and see what it is. If it's 1, yes, the congruence is solvable, and yes, 73 is a quadratic residue. If the symbol is equal to -1, then the answer is no, the congruence is not solvable, and the answer is no here. A is not a quadratic residue. So this discussion, this entire discussion reduces to our, let's say, ability to compute a quadratic symbol. So for the rest of this this video, I'm going to explain how we compute the Legendre symbol. Make it a different one. Maybe let's close this and I continue with the computation.